Welcome to PLUTUS IES, and today we are covering another unit from electrochemistry, that is your Gibbs-Helmholtz equation. So what does Gibbs-Helmholtz equation do? Gibbs-Helmholtz equation serves as a bridge that connects thermodynamics with electrochemistry. Now, why does this equation is so significant in terms of your exam syllabus is that previously, apart when this equation was not introduced, we had a problem while relating if you are having an electrochemical cell, which reactions are feasible or which reactions are not feasible. So how to relate the feasibility of a reaction with respect to the potential. Now, although we already know that the although we know that here, using this particular relation, we are utilizing that the feasibility of a reaction can be explained in terms of minus nf e naught of cell. This is the relation that we already know, but the problem is this relation is only talking about the Gibbs free enthalpy. What about entropy? What about temperature variations? And what about enthalpy? Those are the problems that this particular equation faces. So here we are trying to aim to derive a equation that can fulfill all the requirements that we have in terms of thermodynamics. So, and today we're gonna do that. We will derive the Gibbs-Helmholtz equation and how we get it. So first, before we go into that, since we are talking about thermodynamics of a reaction, in thermodynamics, the work scene defined can be on two parameters. First, the mechanical work that involves change of pressure and volume. Then it comes down to non-mechanical work, which we'll be doing in our electrochemistry, which do not require change of pressure and volume. Do not require pressure and volume. And this is what we need to do. We need to find this particular work done in terms of electrochemistry. So we know for a feasible reaction, the Gibbs free enthalpy is directly proportional to the work done that we are doing. Now, since work done is directly dependent on the potential, the ability to carry charge from one point to another. So, for Gibbs free enthalpy, since at delta G naught, we can write that the total potential can be represented as the multiplication of the total charge that the solution or the electrochemical cell carrying multiplied with the potential difference. Potential difference. Now, potential difference can be defined in terms of your E naught of the cell, while charge is represented in terms of farad. Now, since in a molecule, in a reaction, large number of moles of charge can be displaced, so we can take n number of moles of charge that is being that are being carried in the solution, or the total number of electrons that are being donated or accepted in the solution by NF. So, with this, we can find that the delta G naught now can be represented as negative, or work done is negative, so it will become minus of nf of E naught of the cell. So this is our first relation that we have got. Now, to relate it with thermodynamics, we can differentiate this particular thermodynamic factor with respect to temperature at constant pressure. So why we are doing this? Because as per thermodynamics, the change of standard Gibbs free energy with respect to temperature at constant pressure gives us what? Since we are doing gives us change of standard entropy. Since this is a non-mechanical work, we are taking into account constant pressure. This will be minus nf of E naught of cell. Now, charge is a constant value, so here it will be E naught divided by temperature. at constant pressure. Here, this right here is called as Kt, or temperature coefficient of the cell. Temperature coefficient of the cell that gives us the effect of temperature on the EMF or the feasibility of a reaction. So if your Kt comes out to be positive, a positive Kt means that E naught of the cell increases with increasing the temperature. So that means the reaction was initially non-spontaneous and it required some amount of temperature for the reaction to become feasible. So a positive value of Kt corresponds to non-spontaneous reactions. And for non-spontaneous reaction, the process is endothermic. That means you need to provide some amount of energy from the outside. Well, if the Kt comes out to be negative, that means if you are using E naught of the cell, it will decrease with increase in temperature. That means the process was spontaneous. It already had enough amount of energy to carry out the process, and this corresponds to an exothermic process. But so far we have still no idea regarding the enthalpy of a reaction. So we know from the thermodynamic relation that Gibbs field enthalpy is given by enthalpy minus T delta S naught. Putting in the values, delta H naught, delta G naught plus T delta S naught. We already know the value of delta G naught, that is minus NF E naught of cell, plus T, putting in the value of delta S naught, NF Kt at constant pressure. Now in this reaction, let's try to separate out the things which are appearing common. So here I can write delta H naught, taking minus NF common, NF, it will become E naught of cell minus T d E naught by dt at constant pressure. And this equation right here, it explains the enthalpy of the reaction, the temperature dependence, as well as the entropy of the reaction. And this particular equation that we have derived right here, this is called as the Gibbs-Helmholtz equation. So I hope now you understand why this equation is used, what is its significance, and how it bridges the electrochemical reactions feasibility with the thermodynamic parameters like enthalpy, Gibbs entropy, etc. So in case you like the video, please like, share and comment and subscribe to the channel. And thank you for joining us for today. In case of any doubt, you can add it to the comment section or any new topic that you want us to make the videos on. So for the time being, keep learning.